Having examined the mechanism of imine formation, we are now prepared to tackle the mechanism of the reverse reaction, namely imine hydrolysis. So in the presence of water under acidic conditions, imines are hydrolyzed to give back the aldehyde and the primary amine, and an example of this reaction is shown on the screen. And the mechanism is essentially the reverse of imine formation, but there are a couple of subtle differences that we'll go over as we go through this mechanism. Okay, so step one is the exact reverse of the final step of imine formation. It is the protonation of the imine to generate the iminium ion. The only thing I want to say about this step is we are now going to use H3O plus as our acid. Because remember, we're in the presence of water under acidic conditions. We've got aqueous acid, and aqueous acid is also known as H3O plus. The nitrogen has a lone pair on it. It picks up a hydrogen from the H3O plus. You break the oxygen-hydrogen bond, putting the electrons onto the oxygen. Okay, now step two is the nucleophilic attack of water on the iminium ion. So treat the CN double bond. I could have drawn another resonance structure with a positive charge on nitrogen, but treat the CN double bond just like a CO double bond. So you can add to the carbon of an iminium ion just like you can add a nucleophile to the carbon of a carbonyl. The nitrogen here already has a positive charge in it, so when we break the CN pi bond and put the electrons on nitrogen, we are ending up with the nitrogen having no charge. Of course, as you have the oxygen attacking the carbon, it still has both of its hydrogens, so at this point, the oxygen is still forming 3 bonds and still has a positive charge. But again, there's nothing particularly unfavorable when you look at these two steps together, because we start out with H3O plus and we're generating something after 2 steps that has essentially the same strength acidity. Step 3 now, I like to say, is an intramolecular proton transfer from oxygen to nitrogen. Okay, so you have a neutral amine in this intermediate, and in neutral amines, the nitrogen is moderately basic. You have a protonated oxygen, which is a strong acid. So we have a basic site and an acidic site in very close proximity, so they are simply going to react with each other as quickly as possible, and that has the nitrogen from the basic site just pulling the proton off of the acidic site and shifting it over. So an arrow from the nitrogen to the hydrogen, and then another arrow breaking the OH bond and putting those electrons onto the oxygen. This will be a very favorable proton transfer step, and the fact that I have those equilibrium arrows drawn as such is supposed to indicate that. So if you're really thinking about this, what we have actually done is we have skipped the neutral carbanolamine. In order to get to the neutral carbanolamine, we would have had to have some external base come in and remove the oxygen, the hydrogen that's bound to the oxygen, and then we would have to have some sort of external acid donate a hydrogen to the nitrogen. That can happen, that probably does happen, but in this case, carrying out the proton transfer reaction intramolecularly is probably how it goes, probably going to be faster, and there's no reason why we have to include an intermediate that's going to be very short-lived under the reaction conditions anyway. So I am happy with us going directly from the cationic oxygen to the cationic nitrogen. In step 4 now, we have set up, by protonating the nitrogen, we have set up expulsion of a leaving group. So in the forward mechanism, we had to protonate an oxygen to expel it as a leaving group. Now we are setting up protonating a nitrogen to expel it as a leaving group. So we break the carbon-nitrogen bond. We take those electrons, put them onto the nitrogen, which is the more electronegative element, and then that gives off a molecule of methylamine, CH3 and H2. What is left behind when you expel a leaving group under acidic conditions is a carbocation, and this carbocation is a resonance stabilized oxocarbocation. So at this point now we're looking at something very similar to hemiacetal or acetal hydrolysis under acidic conditions. We have the oxocarbocation, which can also be thought of, if you look at the second resonance structure, as a protonated aldehyde. So to get to the neutral product, we simply have to deprotonate the oxocarbocation to give the neutral aldehyde. Now, what base are we using to deprotonate it? Well, the strongest base that is present under acidic conditions is the molecule of neutral methylamine that we just kicked off in step 4. Okay? Could you use water as a base to do this? Sure, it probably happens. But eventually, that methylamine under acidic conditions is going to get protonated, and why don't we just have it do the work in step 5? So nitrogen pulls off the hydrogen, the electrons go onto the oxygen, we have a neutral aldehyde, and everybody is happy. Okay, so this is a genuine mechanism under acidic conditions. All intermediates in this hydrolysis mechanism have positive charges, and unlike in the forward mechanism, we don't have to worry about keeping the pH high enough to maintain a viable concentration of neutral amine. In fact, for the hydrolysis to go to completion, we don't want any neutral amine present at all, because otherwise it could start the reaction going back towards the imine. And by having it protonated in the last step, we ensure that the concentration of methylamine ends up pretty close to 0. Okay, so that ends our discussion of imines. So we looked at the overview of imine formation, we looked at the detailed mechanism of imine formation, and now we looked at the mechanism of imine hydrolysis. Continuing on our tour of the reaction of aldehydes and ketones with nitrogen nucleophiles, in our next video, we're going to look at what happens if you use a secondary amine as the nucleophile instead of a primary amine.